All right, so quick review before we get into more into logarithms. Okay, so we did all this on Friday. I'm just going to buzz through it as quickly as possible to make sure that we're in good shape. So if this is a function f and this is a function g, and I want to do f of g of 4, do I have to find f of g of x to be able to do that? No, in fact, that would be kind of a difficult process to combine them when all I have, now I'm going to do it eventually, so if you want to do it eventually you can, and then go back and find f of g of 4, but I would probably go g of 4 is 3. I'm going to replace g of 4 with a 3, drop the f, and now f of 3 is
7 minus 15 minus 7. 7 minus 7.
I didn't get that. Let me see. 27 minus 15 minus 7 is 12 minus 7 is 5.
Ah!
So what does that mean? F of g of 4 is 5. And show as much or as little work as you want, but know that if that number's wrong and I don't see even that, then I can't give you any partial credit. But if you had made a careless mistake there and said 7 or whatever, I could look at your work and go, oh, that's a careless error, ... So the more you show, the better off and stuff like this. All right, what about g of f of negative 2? Negative 2 in there gives me 12 plus 10 is 22, minus 7 is 15. So all of that right there becomes a 15. And then g of 15 is a 25, which means if that equals that and that equals that, then all of this is 25. And if you have values like that with composite functions, it's probably easier to go about doing that. But what if you have variables? Then what do I have to do?
Well, you just take, like if it's g of x, and it's just the equation.
So I'm taking, literally, I'm basically doing a substitution, right? I'm plugging that in place of where g of x is in this equation. So instead of having f of g of x, I now have f of 2x minus 5. Now, every year I have somebody on these problems, they go to here and they go, oh, so I need to multiply f times 2x minus 5. And they write the whole f equation down, and then they take 2x minus 5 and write down, they FOIL it all out. Please don't do that. This is saying to do what? Plug that in to my f function. So that, just like 4 got plugged in for x, I'm plugging that in for each x there. So this ends up being 3 times 2x minus 5 squared, minus 5 times 2x minus 5, minus 7. Y'all with me? Now I do need you to clean it up. This is a new function, so we want to write that function as nicely as we can. So I'm going to go ahead and FOIL this out and multiply a 3 in. So foiling it out, I get 4x squared minus 20x plus 25. And then minus 10x plus 25. And then you still got to distribute that 3 in there. So this is not fun, I guess. But it's definitely doable, right? So I end up with a new function, f of g of x equals 12x squared. Add those together, or subtract them, I guess, negative 70x. And then 93 when you add all those 3 together. Right? And if I had done this ahead of time, I could have plugged the 4 into that, but the numbers are kind of large, and if you make an error here, it's going to cost you twice, isn't it? So if it were me, I probably would have done it the way we did it, even if I did look ahead and see that. And then for g of f of x, what am I doing?
The same thing as with that f first.
So I'm plugging the f this time into, I'm replacing that f with all of that, which means to plug all of that into the g function anywhere there's an x. And the g function would be what?
2x minus, so 2 parentheses, the f function minus 5.
All that in there, minus 5. And I can simplify that probably a little more quickly. And I'm not even going to take 2 lines for this. That negative 14 with an additional negative 5, and I am finished with that. Now every year, I probably have a fifth of my students. They'll get to here, and we've just finished up polynomials and factoring, and they set that equal to 0, and they factor it, and they try to solve. Remember, we're not solving this. We are literally just creating a new function. So make sure you just stop when you get to here. Don't try to do too much more. You all with me? All right. Okay, what about this? What are the composite equations if f of g of x and g of f of x are equal, and they both give me x when I plug a number into them? What does that tell me about f and g?
They go to X.
I'm sorry?
They go to X.
They're inverses of each other. And inverses have all those special relationships we talked about on Friday. Mainly being that they are, when you graph the two functions, what do they look like? Reflections over what? Over the y equals x line. So they're going to be reflections over y equals x. What does that mean about the points on one function?
No, it's like opposite.
I know you're saying opposite math means negate it.
Points times negative.
So what does it mean if I have an AB on F? What does that mean?
Negative A.
I got a BA on G. So you're not negating them, you're just switching places. So remember that functions, if they're inverses, any point on one, you could just switch the place of x and y, and that's going to be a point on the other. And when you do that, that's what creates those mirror images about that y equals x. Are you with me? Okay. And it says if two functions are inverses, the graphs will be reflections. You've already answered that. On this one, when I say graph the inverse, what are you going to do if I ask you to graph an inverse? But even before you do that, and that is, you're correct, do the line test. Because if this doesn't pass the horizontal, the vertical, it's not a function. And it does, so it's a function. But if it doesn't pass the horizontal, it doesn't what? It doesn't have an inverse. This passes both, so let's just do what Sunny said. She said, find a bunch of points. I'm going to always find the easier points first, like that's 0, 2. So I'm going to plot 2, 0. And obviously if it crosses the y equals x line, that's going to be a point. And then this point looks like 1.5, 0. So I'm going to plot 0, 1.5. Okay? And then maybe, how about this one up here? That looks like about a negative 1.75. So how about a 5, negative 1.7? And how about this? This looks like a 2.2, negative 5. How about a negative 5, 2.2? And is there any other one? How about this one? This one looks like 2, negative 3. How about negative 3, 2? And at some point, I'm going to get enough of these plotted to where it kind of makes sense. You might want even another one there. How about negative 1.5 up 4? How about 4, negative 1.5? If you plot enough of these, it's not going to be too hard to sketch your inverse. Yeah, with me? And then what about G?
That's not a function, is
It is a function because it passes the vertical line test, but it doesn't have an inverse function because it didn't pass the horizontal line test. So I said find the inverse of the G function. There is no. Now, you will read in some books, hey, there's an inverse, it's just not an inverse function. And that is true, but since we're in Algebra 2, we're talking about inverse functions. So this does not have an inverse G function. It would have an inverse G relation, and that would be this weird looking thing that kind of is a reflection, but we're not talking about that in this course. So we would say that does not exist. The inverse G function wouldn't exist. And then if I ever get down to like 9 and 10 and say, hey, I want you to find the inverse function from the equation, not the graph, but from the equation, then what would you do?
You replace the x with the y, or you switch the x
Okay.
with the y.
Yes, and before you even get started, you could say, well, it's an odd number, so I'm probably in good shape. But if there's an even number, what does that tell you? It's not going to have an inverse. And why is that again? Because what? Actually, that's true, yeah. If you know that it's a parabola, you're thinking about the graph, and that wouldn't pass the horizontal. But even if you didn't notice that, at some point, when you switch the x and the y, think about it. When I replace that y with an x and that x with a y, what do you have to do to solve this?
Square root.
At some point, you're going to have to square root. And what happens when you square root an even? or it doesn't even matter about the even, but when you square even root something, you get an absolute value, which eventually gives you plus or minus. And that blows up your definition, right? Because the definition of a function is each x gives you one y, but if you have a plus and minus in front of it, that means each x gives you two y's, the plus and the minus value. So I just remember, hey, if there's a 2 there, I'm not even going to bother. I'm going to say the inverse of g does not exist. But here I can do it. So that y becomes an x, that x becomes a y, and if there's more than one x, change them all to y's. All right, and then you got to resolve. So what do?
X plus 5.
Add a 5,
Under 2.
divided by 2 gets you to here. Cube root both of them, and you don't get a plus or minus on a cube root, do you? So if that's y, I'm going to go ahead and write it like this. F inverse of x instead of y equals that thing. And I would probably let you skip the rationalizing on this, but if I were to rationalize it, what would I do to rationalize a cube root of a 2?
5 by cube root of 4.
Yeah, I need a cube root of 4 on the top and the bottom, which ends up giving me the cube root of 4x plus 20. And on the bottom, I get cube root of 8, which is just a regular 2. All right, and then number 11 says, determine some different ways that you could check or determine whether or not these two functions happen to be inverses. We talked about this at the very end of the day, and do you remember them? What's one way I could determine if these were inverses of each other?
Oh, set them equal
Yeah.
to each other?
No, but you could just find the inverse of one, right? Why don't you just ignore this for now and say, let's just find the inverse of this. If you find the inverse of that and it ends up looking like this, or you could make it look like that without breaking rules of algebra, then they must be inverses, or vice versa. Right? So if you want to, change that to an x, change that to a y, add the 5. What do you do to get rid of a 2/3? Multiply both sides by a 3/2. Cancels that out. Is 3/2 times x plus 5 the same as that?
Yeah.
First glance, it doesn't look like it, but then when you multiply it in, you get 3/2 x plus 15/2. Yep, sure enough, that is the same thing. So yes, they must be inverses. Now, what's an even better way, I think? What's the definition of an inverse? What's the definition? We already went over it. What's the definition? F of g of x is g of x is x.
So you can just do a composite.
Yeah, so let's do f of g of x. So take the g, plug it in there. So I get 2/3 times all of that mess minus 5. And when I distribute it in there, I get x plus what? What's that times that? 5 minus a 5. Well, that checked off. That f of g of x gave me x. Now let's check g of f of x. That tells me to take the f of x function and plug it in there. Distribute it in. What does that give me? That times that gives me x. That times that gives me negative 15/2. Drop down the positive 15/2. That cancels also. That's the best way to verify and show that two functions are inverses of each other.
Would you need to do both of them, or if you did one of them, would you know that?
Let me show you why you would need to do both. That's a good question, actually, better than you might think. What if I had this, and g of x was, hold on. Are you with me? Okay. Let me think. Is this right? I think this is going to work. What if I have f of g of x? And that's all you checked. You would take the g function, plug it in here, and what do you get? Square the square root, cancels that out, right? And you get x, and you'd be like, oh sweet, everybody's happy. Yay. But look what happens when you check g of f of x. G of f of x says plug that into there, and what do you get? Square root of x squared, which is absolute value of x. I don't get the same thing, do I? Now, when you're better at graphing, you'll take one look at that and go, oh, that's a parabola. Well, no, you might already do that right now. Down to parabola. But what is this? Anybody know? Left to half a parabola. Well, when I graph a half a parabola on this, part of it looks like a reflection, but it doesn't reflect the whole graph. I'm not drawing this really well, whatever. Part of it looks like a reflection, but it doesn't have this other part. So it technically is not a mirror image. But you kind of knew that, didn't you? How could they be inverses of each other if something with an even power is there, right? This doesn't even have an inverse. But that's why technically you would need to check both in that definition. Now with me, just a quick review of all this. Okay, if you have that down, great. Please, 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 this stuff is not super difficult, but because we're going to be in logarithms for a while, it's very easy to forget we covered it. And then when we get to our test, everybody's busy trying to learn all the logarithm rules, which I got to be honest with you, this is not the easiest subject we cover. It's a new language. You do not speak it. Okay, so you would maybe speak it backwards, so to speak, because you know about powers and exponential rules, but you don't know about logarithm rules, and you just got to relearn them. And I'm going to show you why they make sense a little bit, but you're going to have to relearn them. So with that in mind, don't forget to go back and look at this when it comes to the test. So the next page you see is this big quick reference guide for log rules. You're going to see as I scan through these, there are a lot of them. Okay? All of these you're going to need to know. All right? Now you look at them and at first glance you're like, my brain's full already, I'm not going to be able to do that. Yeah, you are. And some of these actually we don't use that much in Algebra 2. I'm just throwing them out there because they do make your life easy. So all of these you're going to have to know. Of course, these I want you to not know, but these are ones that people misuse. They like confuse this with this. But we're going to attack these one day at a time. Okay? So don't look at, this is going to be a great reference to look back at as you're starting to learn all of it. But now we're going to take baby steps, all right? So just remember that's there. Don't forget on page 39 that you have that at your resources, at your fingertips. And we're just going to slowly jump into logs today. So the first thing I want to talk about is why they invented a logarithm. And I don't know exactly the scenario that happened, but logarithms are not as old as a lot of other things. Like you can go back 6,000 BC and see the Egyptians talking about the Pythagorean theorem. Okay, some of the math is really, really, really old. Some of it, however, is fairly new within the last couple hundred years. And to give you a taste of that, before the dawn of calculators, there were still banks in the 1800s, and people still earned interest. And people were using interest formulas like maybe this. And this was a way to talk about interest on principal, amount you put in your bank, over time. Well, a lot of times, you would have some farmer come in there and go, the banker would say, all right, I'm going to give you 8% on your money per year. And they'd be like, all right, great. I'm going to plug the 0.08 in there. And when I do that and add it together, I get this. And the farmer goes, well, I'm going to give you 10 bucks. That's what I made last year or whatever. And he may ask the banker, how long would it take to double my money? And the problem is, that's a really difficult calculation mathematically without a calculator. I mean, think about it. If I could divide by 10, but think, how do I figure out what power I raise 1.8 to in order to turn that into a 2? Now, some guy actually, and you can see this in your book, you don't see this in textbooks anymore because your textbook's like 30-something years old. I mean, the actual book's not, but when they wrote it was in the 80s. In the 80s, not everybody had a calculator, and if you turn to the back, this is a relic, but this is what I used to do in class. We would turn to the back, what is it? there were log tables. Like, look at this. Like, if I wanted to find a logarithm, I didn't pull out my calculator, I pulled out my tables. I also did this for trig. Like, if I wanted to know tangent of 30 degrees, I'd flip a little bit further, trig functions. And you would look up, literally, it gave you decimal places for all the 6 trig functions. These log tables were really complex to find. But some guy came through there and basically used what limited math they had to, which actually was pretty good considering you didn't have a calculator, to figure out values like this out to 4 and 5 decimal places. And literally spent almost his entire life creating these tables, which now are obsolete, but in their day, before everybody walked around with a calculator, and literally that was, my dad bought a Texas Instruments calculator, and all it did was multiply, divide, add, and subtract, and take a square root. In 1976, it cost him $100. In 1976, my bike cost like $18. I could buy 3 spiral whatever ice cream cones for a quarter. You know, I mean, $100 was like a small. My dad bought a brand new Volvo station wagon. I remember, yellow, in 1974 for under $4,000, and didn't buy the Mercedes because that was crazy money at $6,000. I mean, you think about that. So $100 was a ton of money. People didn't have calculators. People used tables. That's a hard problem. This, not a hard problem. But somebody took this information and turned it into a logarithm. And how did they do that? This was their mentality. If this, and they changed that to an x, if that's a function, and I'm trying to solve for x, and I can't solve for it for certain y values, what if I found an inverse? What does an inverse do? Switches x's and y's. Are you with me? And then resolves. So if I switch x and y and then resolve, then the thing I'm looking for is no longer way up top. Now it's going to be over here, and when I resolve for y, I have a new equation I can solve for. That was the impetus behind actually creating a logarithm. It's to solve values of exponents that were not easy to find. Now, they still had to do the math somehow, but that was the reason logs were created. So, with that in mind, this is an exponential equation. There is its inverse. I'll talk about how we go from here to here, but if they're inverses, what do you think you should know about their graphs? They're reflections about that y equals x. So you tell me, can you graph y equals 3 to the x? I think you can, just by doing what? Plugging junk in? Plug some stuff in. Talk to me.
1.
If I plug a x is 1, then y is 3. What else? 2 would be great, but it's going to give me a 3 squared, which is 9, which is off my page here. What else? A 0, 3 to the 0 gives me a 1. Somebody said -1. What's 3 to the -1 give me? 1/3. What's 3 to the -2 give me? 1/9. What's 3 to the -3 give me? 1/27. 3 to the -4. Is 1 over 81 or 1 over 243 or any of those values of powers of 3 ever going to hit 0?
No.
But they're going to get really freaking close, aren't they? So that's what creates an asymptote here. So exponential growth, exponential anything, exponential functions grow like this. Now, if that's an exponential function and they're inverses of log functions, then log functions should have all the points where these coordinates were just flipped. So instead of having -1, a third, what should I have? A third, -1. Instead of having 0, 1, I should have 1, 0. Instead of having 1, 3, I should have 3, 1. And all these other fractions as well. So when I graph a log function, it looks like this. And you can see that like before, those would be mirror images of each other. Symmetric about the what? Y equals x. Are you with me? So inverses of each other is a huge deal for us because that's how we're going to solve these things. Now think for a second. If I had this equation, how do I solve for y? Do you realize that what you're doing is you're using an inverse relationship? The inverse of a positive 2 is a negative 2. That's why I'm allowed to do it. What do you do when I have something like y squared equals 5? Do you realize that a squared and a square root have an inverse relationship? Now I know it's not an inverse function, but it's an inverse relationship. That's why I am able to do that. Do you know that if I have something like, I don't know, x minus 3 divided by 5 equals 4, what am I going to do to begin solving here? Multiply by 5, why? Because division and multiplication have an inverse relationship. Well, when it comes to solving these, like if I want to solve for x here, the inverse of an exponential is a logarithm. So to get rid of a 3 that's an exponent, I would log both sides. Like square rooting both sides gets rid of squared. If I wanted to get rid of a log, the inverse of a log is an exponential relationship. So I will do what you call exponentiate both sides. All these things, it's just one more step in your algebra growth. But it is kind of a new language, and you got to figure out ways to simplify through all these little rules I'm going to start tossing at you. All right? So first rule of logarithms I need you to know is this. In the land that we live in, the math land that we live in, which is, at least with logs, it's real numbers, we will never, ever, ever, ever log anything but positive numbers. Okay? Only positive. That means no negatives or zeros. And you saw that on the graph. Do you remember what the graph of the log looked like? You remember it? It looked like this. Were there any negative numbers on that graph that you plugged into the log? No, it didn't even exist over here. Did you even plug in 0? I mean, could you plug in a 0? Evidently not, because you never hit 0 on the exponential, which means you never plugged in a 0 on the log. There were literally, the only thing I'm allowed, x values I'm allowed to plug in are positive values. So if you ever see something like log of -1, can't do it. Log of 0, can't do it. Log of -26, can't do it. You cannot log negative numbers. Are you with me? Okay, now, as soon as I say that, there was this guy, he's a genius. He went to, he lives in the Humboldt community. Y'all know the Dr. Gaunt? He went to Cal Berkeley for his undergrad, then got his doctorate, or vice versa. No, he went to MIT for his undergrad, got his doctorate at Cal Berkeley, and he works in the radiology department. He basically he finds ways to decrease radio emissions in x-ray machines to make it more healthier for people. Brilliant guy. And I've been saying, you can't log negative numbers, and he sent me this, Mr. Hurry, I was talking to my daughter today, you know that you actually can log negative numbers. And he sent me this thing, and I have it in your book. If you scroll down way, it's going to blow your mind a little bit, I think. But if you go way down at the end of the log chapter, I put something about how to log a negative number. And there's all kinds of weird stuff like, what are they called? Arguments, little args in there, and all kinds of weird stuff. So if you ever are interested in taking it to another level, you will never see that in any math course in undergraduate or graduate school. But technically you can log a negative number. I was unaware of that because I never learned it in grad school or undergrads. But Dr. Gaunt is smarter than anybody I've probably met when it comes to math and science. Anyway, thought I'd mention that, but technically you can log, but I'm just going to say for the land that we live in, you cannot log anything but positives. Okay, so a couple of rules. Here's a logarithm equation, all right? So this x right here, that's the number that you're logging. And I'm going to talk about what a log is in a second. That's the number you're logging. Has to be positive. Also, this a is the base of the log. That's like a base of an exponent, like an exponential equation might be 2 to the x or 5 to the x. Well, they're inverses, so that would be like the base of the log. The base of the log also has to be positive, but it can't be 1. And there's a reason why it can't be 1 I'll get to later. Now, don't think in your head, well, if it's positive, and it can't be 1, why don't I just say greater than 1? Well, because there's all those values in between 0 and 1. So it can be the decimals in between 0 and 1, or the fractions, but it can't be any of the zeros and negatives, and it can't be 1 or the base. Gotta remember that, okay? Then, this is true if this is true. Why? Because these are inverse relationships. All right? So what you need to know is this. If that is true, if this is true, then this is true. And what we're going to call this is we're going to say log base A of x. That's how you read these. So if I had something like this, how would you read it? Log base 2 of 3. Actually, if it's base 10, we don't put anything. It's kind of understood. But something like this, log base 7 of 4. We'll talk about what that means in a second. And then something like this, log base 2 of 8. Now, if you have that down, and again, all the base values are positive, we're okay. The values that I'm logging are positive, I'm okay, I can do this. But if you ever saw something like this, log base 1 of 4, that can't happen. So I would say D and E. And again, if I saw something like this, that can't happen. So I would say D and E. Are you with me? If I saw something like this, base can't be negative. That can't happen. I would say D and E. So make sure that you know those rules, and then we'll start moving on to another rule. Now, let me give you an example of why this first rule I give you is going to be true. Okay, so do you remember me saying something like y equals, let's just start with y equals 3 to the x. Now, if I told you y equals 3 to the x, if I told you y was 27, can you eyeball that and see what x is? And you can tell that'd be a 3, right? Now, in your own words, describe this to me. Don't just say 27 equals 3 to the x, but describe what x is.
3 raised to the power.
Now, tell me what x is.
It's a couple extra 3s that you multiply by the base.
Okay, that's true.
The number of 3s that are being multiplied.
Okay, I like that a little bit better. You're saying, think of it in terms of a power, because it's a power. I'll get you started. 3 raised to what power gives me what? So really in your brain was thinking 3 raised to what power gives me a 27? And the answer to that is 3. This is a logarithm, would be this. Means the exact same thing. 3 raised to what power gives me a 27? 3. Same thing where this is x is 3, this would be equal to 3. If I gave you this, how do you say this? 2 raised to what power gives me 1024? 10th if you know your powers, right? And you would say x is 10. But as a logarithm, you would say log base 2 of 1024. 2 raised to what power gives me 1024? 10. Well, there's a log rule that lets you do this without thinking about exponential functions. And the log rule says, if you can rewrite, say, the 27 or the 1024 in terms of 3 or 2, like for instance, right here, if I rewrote, by the way, that's a sub 3. Make sure that 3 is down here. If I can rewrite 27 as the same number as the base, or maybe rewrite both of them, then basically all of this part cancels and leaves me just the exponent. If I can rewrite that 1024, the 2 is down here. Rewrite the 1024 as 2 to the 10th. If those two numbers match, essentially they cancel. And I get a 10. Now, your book says this. I want to go one step further. One step further says, if you can write both of these numbers with the same base. Then what you're really doing is canceling the bases out and taking the power over the power. Now you may go, well, that gives me the same thing. Well, it does in these two cases. Right here, power of the 2 to the 10th, the power of the 2 to the first, 10 over 1 gives me 10. And that gives me a lot more freedom now, because now I can do problems like this and problems like this when I don't rewrite them as just 6 and 4, and I can start doing problems like these two. So let's use this rule, and this rule is in your little quick review log sheet that says basically this. If I can rewrite a log so that the base, the number that's down low, I rewrite it and then rewrite the number that I'm logging, and it might not use these same letters, but it basically says, if you can rewrite it like this, the log and the x's, or whatever the bases are, cancel, and they leave you the power over the power. So let's think about that rule and see if we can simplify using this rule. And the more you do these, the better. So right here, can you rewrite 36 and 6 with the same base?
6 to 1,
Okay.
6 and 2.
So that would be 6 to the first, and that would be 6 squared. So since I have the same base, those are the x's, essentially the log and the 6's cancel, leaving me 2 over 1. Now, you might change the 64 and the 4 in the next problem to base 2, but I could use base 4, couldn't I?
Yeah.
So isn't that the same thing as 4 to the first down low
Yeah.
and 4 cubed right there? So the 4 and the logs cancel, 3. What about this next? Actually, we just did this one. But right here, that would be the same thing as 2 to the first and 2 to the 10th. So 10 over 1, which is 10. Now jump down. What about this one?
6 to 1, 6 to 1.
So 1, does that give you a log rule, another log rule? If the numbers ever match, what's it going to be equal to?
1.
As long as it's defined. What I mean by that is, these numbers match. Is that 1? Why not? You have to log positives, right? What about this? These are positives. Why not? That value down there can't be a 1. So that would be a DNE. This would be a DNE, because I can't have negatives and I can't have a 1. But if the numbers meet that quantity, that qualification of the definition, or they're positive but not 1, bottom one can't be 1, then yes, if they already match, 1 over 1 is 1. And then what is this?
0.
Good, why?
Because log is 6 to the 1 and 6 to the 0.
Yeah, you could think about it like that, couldn't you?
And then 0 divided by 1 is 0.
And 0 over 1 is 0. But you know what I'm going to remember? Anytime I'm logging a 1, it's going to be 0 as long as it's defined. Okay? Now, what if it's not defined? Then it doesn't exist. So don't just get it right, because I can't have a -3 there. Same thing as not having a 1 right there. So remember the rules. If I'm logging and the numbers match, then it's just 1. If I'm logging a 1, it's always 0. But again, all these rules fit this right here. Okay, so let's change it up a little bit. What about that log base 8 of 16? Nice. So if that 8 and that 16 could be written as a base 2, can they be written as a base 4? I don't know how to do that without like fractional exponents. So don't even bother. So if I can write them as a base 2, that would be, and again, the 8's low. So that would be 2 cubed. That's 2 to the 4th. What's my rule tell me?
4 over 3.
Must be equal to 4/3. You with me? What about this one?
3 to the 2nd and 3 to the 6th. I mean 3 to the 5th.
3 to the 5th.
Excuse me.
Right? Which
Yeah,
is?
I haven't confused me. 5 half.
I was testing you, son.
Sorry.
Are y'all seeing this? Now I can ugly this up worse. What if I gave you log square root of 3 of cube root of 9?
No.
Can I rewrite these with the same base?
Yes.
Cube root
let's remember what we know. What is that? 3 to the what? To the 1/2 power. Good, are y'all seeing that?
Yeah.
What is that?
3 to the 2/3.
That's like 3 squared underneath, so 3 to the
2/3.
2/3. And then what do you end up with then? 2/3 over 1/2, which is 4/3. Y'all seeing that? What about this one? What if I had log root 5 to 1 over 125? So this is log base root 5 of 1 over 125. Can I rewrite those as base 5? Now, by the way, this is not like real life. This is just like me tormenting you. But I will do that on a test for little small problems to see if you really know your rules. So how can I rewrite that as a base 5? 5 cubed won't do it on the bottom though, so how do I make it just 5? What's a 5 cubed on the bottom? 5 to the negative 3?
Yeah.
Does that make sense? Because like 5 cubed in the denominator is 5 to the negative 3, and my rule only allows me to have something to a power, not 1 over something to a power. So I have to make it fit my rule. So 5 cubed there becomes 5 to the negative 3, and that's a what?
1/2.
5 to the 1/2 power.
Negative 3 divided
See how now it's fitting? Remember, my rule is log. I have to have the base and the base there and there, and then I can have any power I want, but I can't have a 1 over something. So I can't write it as 1 over 5 cubed. I have to write it as base, base, power, power. And if I can do that, then all the bases and the log cancel, and I get negative 3 over 1/2, which is negative 6. Are y'all seeing that? Yeah. Does it fit this? But you got to make it fit that. Does it fit it if I have that in there? No, that would be 1 over x to the n. Doesn't fit it yet. So you got to make it fit, and then once it fits, just put that over that and simplify. And you're going to see a bunch more of these on your work. All right, let's see where we are. So we've talked about a lot of these, and literally we've already talked about a lot of these rules already, right? Anytime you log a 1, you get a 0, as long as b is good. Anytime they match, you get a 1. We've already talked about that, right? And then we said if you have a log, what are the conditions of a and b? The base, and again, I'll switch the letters up, but the bottom number has to be positive, but not 1, and the number you're logging has to be positive. And then what, oh, I didn't mention this one yet. This is another log rule that I'll get to in a second. All right, but let's jump to this. Didn't we say log base a of a to the x was x because x over 1 is x? But also log base a to the y of a to the x cancels x over y, right? And this one's very rarely used, so I'll get back to that later. But really, what it's saying here is that I could take these and leave them alone, but you still have this left. But we got to get to some more stuff before we get to that. And then, by the way, anytime you have a 10 on the bottom as the base, we call it the common log. And when you have a common log, you don't show 10. So I would write this like log of 10. I'm sorry, log of b. And that would be understood that that's a base 10. And we call that the common log because we count with our fingers. You know, 10 fingers. It's base 10, our number system. So it's kind of understood. And until recently, and I mean recently, until like 10 or 12 years ago, all your calculator had on it was a log button and a natural log button. That's an 84 button. All it had was a log and a natural log. And we'll get to the natural log later. And you couldn't even do like log base 2 on your calculator. You had to change it. But now the calculators, you're allowed to do any log base that you want, and they have it programmed pretty well that way. So far, so good? Okay, so all I have here are just more random, weird problems, and that you could practice on if you wanted to. And I will caution you on a couple things. Like right here, this says, right here, log -4 squared is the base of -4 to the 10th. What would that 10 and that 2 have done to those negatives before you ever got to logging them? Made them positive. So could you log these then?
Yes.
Yes, and you could go 10 halves, which is 5. But here, that 5 is not going to do that, is it? So if it's going to stay negative, then I would say, no, I can't do that. D&E. Here, what happens when I raise them both to the same power? Do I say 0 over 0? No, even though you kind of get lucky because that doesn't exist. But right here, anything to the 0 power gives me a 1 as long as it's not base of 0. And I can't have a 1 down there. And then what is that the same as? It's 10 cubed, right? But what base is that? It's the common log. So what do I end up getting? 3. It's 3 over 1 is 3. All right, now last thing, I got 1 minute, Dad, coming. So real quickly, let me just show you how we can use these rules. You know what? I'm not going to do it. When you go home tonight and you have to solve these, skip those. So if you have to solve an equation with x in it, you're going to skip those. I don't want to try to rush through this. We'll cover this tomorrow.